Bloomberg Audio Studios. Podcasts, radio, news.
Hello and welcome to another episode of the Odd Lots podcast. I'm Joe Weisenthal.
And I'm Tracy Alloway.
Tracy, here's something I know about AI. I don't know much, but here's something I do know.
How to log into ChatGPT?
No, I'm good at that. I'm good at logging into ChatGPT and Claude, and I'm reasonably good at asking questions. No, here's actually something about the business of AI that I know.
Okay.
I know that Nvidia is making a ton of money, and the stock has gone to the moon, and that other companies would like a slice of that pie.
Yes. Yes. That's a good thing to know.
It's like a basic, simple thing, which is that when people think about AI chips, there's literally one company that comes to mind. I know others are involved. AMD has stuff. Intel obviously wants to play others. But there is obviously that one gigantic pile of cash that's flowing to this one company. I don't know if it's still, but at one point it was the biggest company in the world. It was pulled back a little bit. Well, I would say two things. One, other companies would like a piece of that pie. And B, companies that are in the business of building AI models would like to find a way to get cheaper, more efficient, less energy intensive chips so that they don't have to always pay the Nvidia tax.
Do you want to know what I know about AI and semiconductors?
Let's go for it.
Okay, here's the one thing that I know, which is that whenever you have this conversation about NVIDIA, the one word that always comes up is moat.
Oh, yes, moat, yes.
So, you're either talking about medieval castles or you're talking about semiconductor manufacturing. That's when you hear the word moat, because over and over again, people will say it is expensive to make the chips. You need a lot of money for research and development and to set up the fabs. And you need a lot of first-person expertise in building them. And then there's also the network effect.
Yes.
So a company like NVIDIA has this huge moat around its business. The question, of course, is whether or not, getting back to the medieval castle analogy, it is unassailable.
That's right. In fact, in semiconductors seems to be moat after moat after moat, because there's ASML's moat, and then there's Taiwan Semiconductor's moat, and then there's NVIDIA's moat. And so, yes, it's like there's a series of moats. And if someone could overcome these moats or find a way to build a bridge over one of these moats and enter this proverbial castle, that would be very lucrative. We know that many are trying to enter these moats, but it's incredibly costly and capital intensive and difficult, and there are just not many people who know how to do any of this stuff. And so the question of whether these moats can be overcome. But again, there are many businesses that would love to see more robust competition in the space so that their payment is not a tax.
You know, one thing I don't know, and I don't think we've ever done an episode purely on this, but I don't really understand the different designs of chips. So I know that some chips, specifically NVIDIA's, are supposed to be better at AI. They're better at running lots of little calculations all at the same time. And I know there's basic chips that go into your refrigerator or your car or whatever, but I don't really know the difference between what a chip that was designed specifically to run a large language model would look like compared to a standard basic chip.
I don't know anything about chip design. I just sort of imagined someone on using some CAD software, etching little lines in a thing and drawing some sort of circuitry or, placing the transistors.
Actually, a chip design game would be really fun now that I think about it, where you could just draw little things on the square. Okay, anyway.
Well, we are going to learn about how chip design works. We're going to learn about what makes a chip particularly good for the task of training and running inference on these AI models. And I have to say, I really do believe we have the two perfect guests because they are both veterans in this space and they are both active in the attempt to bridge some of these moats and enter the space and bring competition to the industry. We are going to be speaking with Reiner Pope, co-founder and CEO of MatX, as well as Mike Gunter, co-founder and CTO of MatX. It's a new company that's trying to build chips specifically for the purpose of large language models. Both of them have a lot of experience in the space. We're going to get our hands dirty, so to speak, and understand how you build hardware for all this stuff and what makes it win and whether it's even a winnable game. Reiner and Mike, thank you so much for coming on Outlaws.
Thanks. Happy to be here.
Pleasure to be here.
So why don't you tell us, what does a chip designer do? I know I have this completely cartoonish view in my head that cannot possibly be right of someone on a big screen using some CAD software to sort of, figure out what's going to be etched in that wafer of silicon. What is the job of chip design?
So maybe this is best told by what is the story of chip development from the beginning of a project to the end of it. So there's a range of different ways this can go, but there's a lot of things that are in common. So generally, a chip design team is at the low end, maybe 30 people up to many, many thousands of people at the high end. And as the project typically runs for somewhere in the range of 3 to 5 years from conception to actually shipping to customers. And so over that time, what we see in the life cycle is we tend to start with a small team of architects. If you think of designing a house, the team of architects, they're the people who decide what rooms go in here, how many bedrooms, how many bathrooms, what are the flows between them, how do people walk through the corridors, and so on. The coarse-grained design of the chip. In the chip itself, that is what kinds of components at the high level we have. And then after that initial exploration, this moves then over to the micro-architects. These are the people who are designing the individual rooms. What are the components that go in the individual rooms? So at that point, everything we've done so far is a design stage thing. This is done in documents, spreadsheets, and it's a verbal and human communication form. But beyond that, that's when it starts to actually touch the computer in a more meaningful sense. And so the micro-architects will hand over to the logic designers. They are the people who are actually writing code. So even though you think of chips as being this very physical thing where there's wires and gates and everything, the way we transmit this information to the computer is actually writing code. We write Verilog that expresses the design of the chip. So that's what the logic designers are doing. That's an extended period of time building out all of the different, matrix multiplies, memories, circuitry that connects to the outside world, and so on. And then the output of all of them is this Verilog piece of software code that gets then compiled by a computer down to a set of gates, which are logic gates and OR gates and so on, and then wires that connect them together. That's the netlist. This file, then there's a few more stages still coming here. This file gets handed off to physical designers who, again, work with CAD tools to convert this kind of logical description.
I was right. So someone is using CAD tools.
Absolutely. There's a CAD tool, but it's only a part of the job.
Okay.
So the physical designers are converting the sort of logical description into a physical placement. So where do each of these gates go? Now, there's 200 billion logic gates on a chip, so a human is not going to be placing all of those manually. So there's a huge amount of software assistance here. But what the human is doing is providing oversight through this process and saying, I've done this a ton of times before. This placement kind of looks wrong. It doesn't match my heuristics, and so I can probably do a better job here. So that's the physical designers, and the output of their work is actually, eventually you get a polygons. So basically an image saying, here is the thing that is going to get etched onto a piece of silicon. So that file is ultimately a huge, really big image in some form, a bunch of polygons on it. It gets handed over to a manufacturing company such as TSMC. They spend maybe 4 or 5 months initially creating a mask set. So those are the templates or the stencils that will be used to stamp out many, many copies of the chip. And then stamps out many copies of the chip, you get a chip back. This is typically about 2 or 3 years after you started the project, you get chips back. And now you have a bring-up team who puts this chip into a whole board and connects it to power and electricity and starts testing it. And then after another 6 to 12 months, or maybe even more, eventually you actually can hand this over to customers. There's maybe just 1 or 2 other things which are not in that flow, but very essential to call out too, are because of this whole process taking so long, especially the manufacturing, we also have very large teams of verification people. So these are the people who, before we actually send it to manufacturing and pay $20 to $30 million of manufacturing, we have a substantial team doing a lot of testing. And this is software-based testing, so writing tests in the same way a software engineer might to make sure that the functionality actually works as intended.
To underline the comparison to ordinary software, which Reiner touched on, we're writing code, but it's on super hard mode. So if you have a software that's deployed via website, you can fix a bug in 10 minutes at basically zero cost. Whereas in our case, the reason that we have a large team of people doing verification, making sure that what we've done is correct, is that it's potentially 4 months and $30 million for every mistake that you let through. Likewise, there is software, but it's a relatively small fraction of software that's very performance critical, where you want the code to run as fast as possible. But in some sense, every line of code that you write in hardware has an impact on the overall performance of the product, because every line of code ends up getting embodied in silicon, and every line of code affects the eventual performance. So it's kind of coding, but on hard mode.
So I intuitively understand the importance of getting the software right, but why does placement on like the actual chip or wafer, why does that matter? Are you trying to make it more efficient? Are you trying to reduce the rise time? Or why does it matter where the little bits and bobs are placed, to use the scientific term?
Yeah, you're right that reducing the rise time is a massive issue. And, fundamentally, the issue is that chips, at a very abstract level are composed of, or at a somewhat concrete level, really, are composed of transistors and wires. And the placement has a dramatic effect on the length of the wires, which has a dramatic effect on both the performance of the chip and how much you can fit. In terms of the impact that this has on the quality of chip that you produce, wires have over time not been shrinking in the same way that transistors have. And so getting the wiring right, which usually means getting the placement right, has become more and more important over time.
Can chips be beautiful? I know code can be elegant, and some people will say certain code is beautiful, but have you ever looked at a semiconductor and been like, oh, wow, that's really nicely put together?
For me, I think absolutely yes. This is like why I work in this space. Is I just really like geeking out on the design of things. But to me, what beautiful for a chip means is that it kind of does exactly what it was designed to do, and no more, no less. Obviously, less would be a bit of a disappointment, but often if it does more, you think, well, maybe I designed it for slightly the wrong purpose or something like that.
I think this is a good seg into getting into your business specifically. So we all know that so much of this AI is powered by these Nvidia GPUs, but Nvidia GPUs have been used for a long time for many things that do not have anything to do with large language models or the specific AI applications that people are excited about today in 2024. So for a while the video games is obviously the big one for decades and decades. And then there was like 5 minutes where people got really excited to use them for Ethereum mining. And now everyone's really excited about their use for artificial intelligence and large language models and some of these other generative AI applications that people are excited about right now. Why don't you tell us maybe the sort of idea behind MatX, but specifically what you were both doing when you were at Alphabet or Google, which, it has its own chips. I believe it has something called TPUs. What was the project at Google? Why did Google find it necessary or a good business to start building their own chips for in-house purposes? And then why did you feel the need to then leave to build what you're building now for LLMs specifically?
Yeah. So what Google was seeing, and this was at this point some time back, more than a decade ago, they were seeing that the use of artificial intelligence, LLMs were not a thing at that point,
right,
was going up, and they were worried about how much money they would have to spend on traditional, it would have been GPUs at that time. Mm-hmm. And so they built a very specialized chip to do neural nets, and that chip specialized on matrix multiplication. So they put in a structure called a systolic array, which they definitely didn't invent. It existed, has existed from the 70s, that is especially good at doing matrix multiplication. Now, after that, NVIDIA has added a similar structure into their chips. And the initial Google TPU was an inference-focused only chip, and then they have subsequently made chips that can be used for both training and inference. And I guess now's a good point so the very last thing that I was doing at Google, I was on the TPU team, and Reiner was on the large language model team, and it's probably good to have him sort of tell the story from here.
So I mean, what we were seeing, and this is what we personally were seeing, but Google was seeing more generally as well, is just large language models are a thing. There was this period of time between GPT-3 and ChatGPT coming out. GPT-3 came out in 2020, and so people who were very plugged into the field recognized the importance of it, or at least to some extent recognized the importance of it back then. And so there was this push to, everyone wanted to create their own large language model that was better than GPT-3. And so, I mean, at the time I was on the large language model team, we helped training Google Palm, and we were using thousands of TPUs for that. And one of the things we were saying is, well, look, what does it cost to deploy this in Google Search? There's quite a lot of search queries. I think the public estimates are about 100,000 of them per second. If you multiply out how much each query costs, and if you want to run that on large language models, that's a lot more expensive. And then also, if I want to train a model that's 10 times bigger than my current model or 100 times bigger, suddenly these models have just moved from costing, $1 million or $100,000 to train to tens of millions and hundreds of millions of dollars. And so the overall goal was, can we make it cheaper by any way possible? So of course, there's algorithmic approaches. There's a lot of opportunity on the algorithm and research side, but then the other really big lever is just making better hardware. So one of the things we were looking at was trying to make Google's TPUs better for large language models. What led us, actually, I mean, this is personally about Mike and me in this case, but what led us to leave Google to make MatX was we saw that we believe that there is some opportunity to make chips substantially better if you're only looking to focus on large language models. And so the chips that were designed pre-GPT-3 and especially pre-ChatGPT try to do a really good job on small models as well as a really good job on large models. And so what you find is that the circuitry in those chips, there's a bit of circuitry for what you need for small models. There's a bit of circuitry for what you need for large models, also for maybe embedding lookups. There's 3 or 4 different kinds of workloads, and all of them take some of the real estate in your silicon. And so if you really want to make the best use of the real estate, you should just focus on the thing you care about most and hope that there's a big market there. So that the game and what we decided to do, and we see some others deciding to do as well, is to really try and focus on just the one workload that seems like it's going to become a $100 billion or a $1 trillion industry.
I know there's always this sort of cliche when talking about tech. They're like, oh, Google and Facebook, they can just build this and they'll destroy your little startup because they have infinite amount of money, except that doesn't actually seem to happen in the real world as much as people on Twitter expect it to happen. But can you just sort of give a sense of maybe the business and organizational incentives for why a company like Google doesn't say, oh, this is a $100 billion market. Nvidia's worth $3.5 trillion or $3 trillion. Let's build our own LLM specific chips. Why doesn't that happen at these large hyperscaler companies that presumably have all the talent and money to do it? So
Google's TPUs are primarily built to serve their internal customers. Mm-hmm. And Google's revenue, for the most part, comes from Google Search. That Google Search, and in particular from Google Search Ads. Google Search Ads is, a customer of the TPUs. Mm-hmm. It's a relatively difficult thing to say that hundreds of billions of dollars of revenue that we're going to make a chip that doesn't really support that particularly well and focuses on this, at this point, unproven in terms of revenue market. And it's not just ads, but there are, a variety of other customers. For instance, you may have noticed how Google is pretty good at identifying good photos and doing a whole variety of other things that are supported in many cases by the TPUs.
I think one of the other things too that we see in all chip companies in general, or companies producing chips, is because producing chips is so expensive, you end up in this place where you really want to put all your resources behind one chip effort. And so just because the thinking is that there's a huge amount of return on investment in making this one thing better rather than fragmenting your efforts. Really what you'd like to do in this situation where there's a new emerging field that might be huge or might not, but it's hard to say yet. What you'd like to do is maybe spin up a second effort on the side and have like a skunkworks to see how it works.
Yeah, that's right. That would be my idea. Just to let Reiner, just let the two of you go have your own little office somewhere else.
Yeah, just organizationally, it's often challenging to do, and we see this across all companies. Every chip company really has essentially only one mainstream chip product that they're iterating on and making better and better over time.
To what degree is chip design driven by the customer? And what I mean by that is, so the TPUs at Google were developed to handle Google's internal workloads. But at other chip designers, to what degree will customers come and basically do a reverse inquiry and ask for a specific chip? Or what does the dialogue between customers and the big chip designers actually look like?
Yeah, it's a fun interplay of, I want my provider to do a good job, but I also don't want to leak my IP too much. So you can see how this played out so Mike was talking about through the development of the TPUs, which were publicly announced in 2016. And around the same time, Nvidia's first GPU with the Tensor Core, so that was the first GPU that was really focused on matrix multiplication, that was the Volta generation, came out at about the same time. And some of this actually was a result of when Google had this recognition of, look, matrix multiplication is so important, we need to make it really better. They simultaneously worked on it themselves, but also went to NVIDIA and said, we're not telling you much, but can you do better at matrix multiplication? And so that was enough for NVIDIA to go on. The first generation, they made a pretty good attempt, but if you talk to people at NVIDIA, they'll say that actually the second generation of the Tensor Core, which was in the Ampere generation, was where they really nailed it. So when it's big enough, you sometimes see these customers coming and saying what they want, but they'll try and disguise what they're asking for, or not giving you the absolute minimum amount of information to help a vendor make what they want without revealing too much about their IP.
Let's get to MatX. Tell us the product that you're designing and how it fundamentally will differ from the offerings on the market, most notably from NVIDIA.
Yeah. So we make chips and in fact, racks and clusters for large language models.
Okay.
So when you look at NVIDIA's GPUs, you already talked about all of this, the original background in gaming, this brief moment in Ethereum, and then even within AI, they're doing small models and large models.
Yeah.
So what that translates to you can think of it as the rooms of the house or something. They have a different room for each of those different use cases. So different circuitry in the chip for all of these use cases. And the fundamental bet is that if you say, look, I don't care about that, I'm going to do a lousy job if you try and run a game on me, or I'm going to do a lousy job if you want to run a convolutional network on me. But if you give me a large model with very large matrices, I'm going to crush it. That's the bet that we're making at MatX. So we spend as much of our silicon as we can on making this work. There's a lot of detail in making all of this work out because you need not just the matrix multiplication, but all of the memory bandwidths and communication bandwidths and the actual engineering things to make it pan out. But that's the core bet.
And why can't NVIDIA do this? So, NVIDIA has a lot of resources. It has that big moat, as we were discussing in the intro, and it has the GPUs that are already in production and it's working on new ones. But why couldn't it start designing an LLM-focused chip from scratch?
Right. So you talked about NVIDIA's moat, and that moat has two components. One component is that they build the very best hardware. And I think, that is as the result of having a very large team that executes extremely well and making good choices about how to serve their market. They also have a tremendous software moat. And both of these moats are important to different sets of customers. So they're a tremendous software moat. They have a very broad, deep software ecosystem based on CUDA that allows it.
Oh, yeah. I remember this came up in our discussion with CoreWeave.
Yeah.
And so that allows customers who are not very sophisticated, who don't have gigantic engineering budgets themselves, to use those chips and use NVIDIA's chips and be efficient at that. So the thing about a moat is not only does it, in some sense, keep other people out, it also keeps you in. So insofar as they want to keep their software moat, their CUDA moat, they have to remain compatible with CUDA. And compatibility with that software moat, compatibility with CUDA, requires certain hardware structures. So NVIDIA is has lots and lots of threads. They have a very flexible memory system. These things are great for being able to flexibly address a whole bunch of different types of neural net problems, but they all cost in terms of hardware. And they're not necessarily the choices to have those sorts of things are not necessarily the choices, in fact, not the choices that you would want to make if you were aiming specifically at an LLM. So in order to be fully competitive with a chip that's specialized for LLMs, they would have to give up all of that. And Jensen himself has said that the one non-negotiable rule in our company is that we have to be compatible with CUDA.
This is interesting. So the challenge for them of spinning out something totally different is that it would be outside the family. And so it's outside the CUDA family, so to speak.
And meanwhile, you already have PyTorch and Triton waiting in the wings, I guess.
So why don't you tell us a little bit more about the business of LLM chips specifically? Because there's a lot of questions one question is you have all these people in Silicon Valley who seem motivated by the idea of AGI, that's the goal, that we're going to have super intelligence one day, maybe thousands IQs into hundreds of thousands one day that'll make us all seem very dumb, etc. Are you implicitly making a bet by your company that it'll be LLMs that will get there? Because as you mentioned, there are other algorithmic ideas. There are other ideas for how you might be able to expand intelligence. How much of your company's bet is the idea that the future of generative AI, or as we know it, is going to be along the LLM pathway?
One of the core things, I think there's two core ingredients of the LLM pathway.
Yeah.
One so far is the transformer architecture, which is a model architecture and was substantially better than the things that came before. But the other one, and that actually has a much longer history, is the scaling hypothesis in general.
Say more about that.
There's a general observation which has been widely recognized for a decade or more that if I'm training a neural net or some kind of AI model, if I want to make its quality better, I make it bigger. And so what does bigger mean? Bigger means I have to spend more compute training it. Bigger means I have more neurons. Those are the loosely analogous to the sort of processing power in a human brain, although the analogy is weak. If I make my model bigger, I get better quality. That's a sort of simple qualitative thing to say. And that's been true for a really long time in these models. So the advantage of that, or the thing that we've seen really recently, is we've seen this turned up to 11. So around the time when GPT-3 came out, so in 2020, a paper was published called Scaling Laws. And so this took this qualitative observation and made it quantitative and said, actually, we can even fit an equation to it. And so that gave people a lot more conviction to it. And this is what led to the people saying, well, if I have a better model, I can solve more problems with AI than I could before. And so every time I spend 10 times as much training on it, I unlock new use cases. And so that's what led to this craze. And the remarkable thing is that while there are these diminishing returns, I have to spend 10 times as much computing power to get some improvement. Beyond that sort of logarithmic scale, we don't see as yet any plateauing. And so it seems like there continues to be opportunity here. So the key thing is this scaling hypothesis or scaling laws in general that are causing these models to grow. And then, as a hardware provider, what you might look at is you might say, that's the thing I really want to bet on. I want to bet on the growth of models. And now it's a little more in the details, but the thing you actually have to bet on is the growth of matrix size, which is very strongly correlated with the growth of models.
Okay, just to hammer this point home, if more AI was learning from stuff like self-play or synthetic data rather than scraping the internet, would the design of the chips have to take that into account? Like, how would the chips vary between those different learning styles?
Yeah, so in general, when you're building a chip, you have to make it programmable because you're going to make this chip and you'll ship a new version every 2 years. But what people want to do with the chip is going to change every month or so. So it has to be programmable to some extent. So that's true for all of the chips that anyone ships. And so there's different scales of programmability and what kinds of changes you need to adapt to. So the changes in kind of the way you feed it data, that's maybe on the very, very outer layers it doesn't affect much of the core of the chip. And so those kinds of changes tend to be some of the easier changes to adapt to. The things that then become a little harder to adapt to is if I'm substantially changing my model architecture. So a small change might be maybe I change the number of layers, or I reorder some of the layers in my model, or maybe I use the same ingredients but shuffle them around in some way. A bigger change would be that, say, okay, I'm actually going to throw out all of these ingredients and use a completely different set of primitives. And that's often that last step is the one that would really kill you if you're betting very much on a particular set of ingredients.
So an example of a potential different set of primitives that are used in other models that aren't used in LLMs are, we made mention of these embedding things that are used in recommender and ad models. So Facebook has talked about building special purpose hardware to support inference on those kind of models. Mm-hmm. They have much less emphasis, relative emphasis, particularly on matrix multiply. Another possible direction that model architecture could go that would be different and bad for a chip designed for current LLMs would be, instead of having very large matrices in about 100 layers, you could have much smaller matrices, but 10,000 layers. And that would demand a different sort of design to be good at that kind of model. So a bet that looks good given the modern history of neural nets is that matrices will get larger over time.
You talk about scaling laws. And so everyone talks about, okay, computation power, energy efficiency, et cetera. And I never know if they're true, but then sometimes like you read these stories, they're like, oh, Sam Altman wants to go around the world and raise like $5 trillion to like build his own semiconductor fabs and have the entire architecture because that's like what it's going to take. What about the data side? Because this is another thing people talk about, the data wall, that, there's only one internet to scrape. And then, after that, what if you're not there at AGI yet? Again, I know you're solving for the hardware side, but when you think about risks going forward along the LLM pathway, what's your perspective on, well, what happens when we've ingested all the data?
So there's two ways you can make a model better. One of them is by training on more data, and the other one is making a bigger model. And these two effects work in a really complementary way. So you can think of it as like having a bigger brain and then practicing more. And so both of these are going to help to some extent. So there's a risk that we hit a data wall. In general, there's been a long history of people predicting walls in different kinds of walls in AI training, and then ingenuity overcoming this. And so I would bet that there's a fairly large amount of mileage to continue here. Tracy mentioned self-training and generating new data. That's the vibe in the industry is that this is a promising direction for sure. But even if you don't bet on that, there's mileage, and it's less attractive mileage, but there is mileage in making the models bigger. So I believe, and I think this is shared by many people, insiders in the industry as well, is that there's at least a few more orders of magnitude available here before we run out of easy engineering knobs to turn. But of course, one of the limiting factors here is just the dollars you spend.
Yeah.
So you have some amount of budget that I'm willing to spend. And I mean, maybe Sam Altman can raise $5 trillion. I don't think necessarily everyone else can raise that amount of money to train a model. And so if you've got a fixed amount of dollars that you want to spend and you want to train the best model, you want to make the best use of the multipliers. You want to make the best use of the dollars you spend. And so that means fundamentally what you're paying for is the flops, which flops is a floating point operation. So the number of multiplies you can do. And then every time I increase my model size or increase the amount of training data I've got, I'm spending more flops. And so flops converts into an intelligence. And then if I've got a fixed budget, really what I want to maximize is my flops per dollar.
I find this so fascinating because there are so many different directions that you could theoretically go in, and so many decisions that need to be made. Do you go after that scale? How do you tailor the design for different methods of data input? Although, as you said earlier, maybe that's one of the easiest things to respond to. But then there are other trade-offs that you have to think about between speed and power consumption and, I guess, area utilization or the placement of all the bits and bobs that we were discussing earlier, and cost effectiveness too. How do you balance all those elements? And are there particular things that you're willing to sacrifice for others?
So different people can choose different targets to go after in the market. And so one target, which you could argue NVIDIA is winning on currently, And one of the reasons that their products are so popular is, as Reiner said, just the amount of flops you can get out of a chip. And if all the chips are roughly the same to make, that translates into flops per dollar. So another target you could also go after would be the time to respond to one user. So to get the answer back, one approach is maximizing the throughput that you can have, and other is minimizing the latency. So kind of the difference between a 747 flying a group of passengers across the country versus an SR-71 getting there in a couple hours, but only bringing one or two people.
Let's talk about the business itself. So, in the old, 10 years ago, someone starting a tech startup, they, get 3 or 4 people in an office, and then they write something up, and then they have a code, and maybe they don't even have to raise any money to do it. And they certainly don't have to depend on whether Taiwan Semiconductor has any capacity at their fab or anything like this. Walk us through the sort of nuts and bolts of what it actually takes to build a chip business from the ground up, both in terms of costs and time and what you have to rely on. We've talked about some of the design element. What are the business side requirements, and what will it take to actually succeed?
So fortunately, and we've kind of referred to this in multiple places, there's a huge ecosystem around designing chips. Okay. So there's a portion you have to do yourself, and there's a portion that you can buy. So the placement of Tracy's bits and bobs, and also the testing that we've talked about, there are EDA, electronic design automation companies that build those tools. Likewise, there are companies that do just manufacturing, so TSMC and their suppliers. And then there are many other companies. So most companies don't go directly to TSMC. So very sophisticated companies like Apple or Nvidia interface directly with them. But most other companies go through ASIC vendors. And so, the most prominent companies in that space are Broadcom and Marvell. And then there are a bunch of smaller companies, a couple that are, close to TSMC are Allchip and GUC. And so they'll do a lot of the work of taking your code and actually getting it placed on the chip. That's often a very good thing to outsource, because the work is somewhat seasonal. You're only ready to do that placement when you're near the end of this 3-year project. And so you kind of don't have work unless you're a massive company for people the whole time. So while that ecosystem means that you don't have to hire a ton of, a huge number of people yourself, all of those people have to get paid.
Right.
And so you do have to raise a fair bit of money. And another big element of thing that you end up spending money on is there are parts of the chip that are very special, difficult to design, and take multiple iterations of taping things out and seeing if they work. So the very high-speed interconnect that connects together chips is an example of that. So those are designed by yet another set of companies, and the design is difficult and fairly expensive because of the need to do multiple tape outs. And so it's fairly expensive to buy that IP. So when you add up the cost of the IP, the cost of the ASIC vendors, services, and then the mask fees that TSMC charges using ASML's mask creation software, you're talking about tens of millions of dollars to bring a state-of-the-art chip to market. The numbers are much lower for a simpler chip without the very high-speed IOs and on an older node. But for an advanced node, it's a pretty expensive process.
When do you think you'll be able to bring your chips to market?
Generally, we see these projects taking 3 to 5 years across most companies. We started on this seriously at the beginning of 24, so about 3 years from there is likely for us.
Tell us about what customers, because I've heard this, we're all trying to find some alternative to NVIDIA, whether it's to reduce energy costs or just reduce costs in general, or being able to even access chips at all, since not everyone can get them because there are only so many chips getting made. But when you talk to theoretical customers, who do you imagine as your customers? Is it the OpenAIs of the world? Is it the Metas of the world? Is it labs that we haven't heard of yet that could only get into this if there were sort of more focused, lower cost options? And then B, what are they asking for? What do they say, like, you know what, we're using NVIDIA right now, but we would really like X or Y in the ideal world?
So there's a range of possible customers in the world. The way that we see, or a way you divide them up and how we choose to do that is, what is the ratio of engineering time they're putting into their work versus the amount of compute spent that they're putting in? So the ideal customer in general for a hardware vendor who's trying to make the absolute best, but not necessarily easiest to use hardware, is a company that is spending a lot more on their computing power than they are spending on the engineering time. Because then that makes a really good trade-off of, maybe I can spend a bit more engineering time to make your hardware work, but I get a big saving on my computing costs. So companies like OpenAI would be obviously a slam dunk. There's many more companies as well. So the companies that meet this criteria of spending many times more on compute than on engineering, there's actually a set of maybe 10, 15 large language model labs that are not as well known as OpenAI, but you might think Character AI, Cohere, and many other companies like that, and Mistral. So the common thing that we hear from those companies, all of those are spending hundreds of millions of dollars on compute, is, I just want better flops per dollar. That's actually the single deciding factor. And that's primarily the reason they're deciding on NVIDIA's products rather than some of the other products in the market, is because the flops per dollar of those products is the best you can buy. But when you give them a spec sheet, and the first thing they're going to look at is just, what's the most floating point operations I can run on my chip? And then you can rule out 90% of products there on the basis of, okay, it just doesn't meet that bar. But then after that, you then go through the more detailed analysis of saying, okay, well, I've got these floating point operations, but is the rest going to work out? Do I have the memory bandwidths and the interconnect? But for sure, the number one criteria is that top line flops.
When we talk about delivering more flops per dollar, what are you aiming for? What is current benchmark flops per dollar? And then are we talking like, can it be done like 90% cheaper? What do you think is realistic in terms of coming to market with something meaningfully better on that metric?
So NVIDIA's Blackwell in their FP4 format offers 10 petaflops in their chip, and their chip sells for ballpark 30 to 50,000, depends on many factors. That is about a factor of 2 to 4 better than a previous generation NVIDIA chip, which was the Hopper chip. So part of that factor is coming from going to lower precision, going from 8-bit precision to 4-bit precision. In general, precision has been one of the best ways to improve the flops you can pack into a certain amount of silicon. And then some of it is also coming from other factors, such as cost reductions that NVIDIA has been deploying. So that's a benchmark for where NVIDIA is at now. You need to be at least a few integer multiples better than that in order to compete with the incumbent. So at least, 2 or 3 times better on that metric, we would say. But then, of course, if you're designing for the future, you have to compete against the next generation after that too. And so you want to be many times better than the future chip, which isn't out yet. And so that's the thing you aim for.
Is there anything else that we should sort of understand about this business that we haven't touched on that you think is important?
One thing, given that this is odd lots, that I think the reason that Sam Altman is going around the world talking about trillions of dollars of spend is that he wants to move the expectations of all of the suppliers up. So as we've observed in the semiconductor shortage, if the suppliers are preparing for a certain amount of demand, and demand, in the case famously of the auto manufacturers as a result of COVID, canceled their orders, and then they found that demand was much, much, much larger than they expected. It took a very long time to catch up. A similar thing happened with the NVIDIA's H100. So TSMC was actually perfectly capable of keeping up with demand for the chips themselves, but the chips for these AI products use a very special kind of packaging, which puts the compute chips very close to the memory chips and hence allows them to communicate very quickly, called CoWoS. And the capacity for CoWoS was limited because TSMC built with a particular expectation of demand. And when H100 became such a monster product, their CoWoS capacity wasn't able to keep pace with demand. So, supply chain tends to be really good if you predict accurately.
Yeah.
And if you predict badly, on the low side, then you end up with these shortages. But on the other hand, these companies, because the manufacturing companies have very high capex, they're fairly loath to predict badly on the high side, because that leads them to having spent a bunch of money on capex that they're unable to recover. So
this is very interesting. This idea that in some part it's a signal. We're not slowing down. We have more and more that we want to do. So if you're anywhere along the semiconductor supply chain, don't start, curbing your expectations or curbing your production, because we want to build a lot more. I'm curious, one last question, I guess, for both of you. You hear a lot of people in the industry say, like, we might just be 3 or 4 years away from AGI or superintelligence, however that's defined. And then you get into a lot of these philosophical questions and ethical questions about, whatever, is the AI going to, what is going to be the role for humans, or is it going to kill us all, or whatever, fear scenario you want. But the two of you, like, how do you see that question? Like, could we hit it in just a few short years where we have something that people agree is, oh, this is AGI? Like, is it short runway or just a couple years away from this? Or does it feel like, no, that's still quite a few years out, if ever?
I think what we have now is incredibly valuable.
Sorry.
Approximately 0, to be blunt.
Okay, thank you.
My P, great things. I mean, I think we kind of already have great things, and we've just gotten the models of this level of quality recently, and we're learning how to use them, and the quality is going up. The fact that we can get a computer to write code pretty well is fairly amazing to me. That you can ask it to tell a good joke in the style of a particular person, and it can do that is also amazing. Yeah.
Well, I'm glad your odds of total doom and annihilation are 0. That makes me feel a little bit better. Reiner and Mike, thank you so much for coming on Odd Lots. I learned a ton from that conversation.
It was a pleasure.
Tracy, there was obviously a ton that was really interesting in that conversation, but I particularly liked the part about incentives of large legacy incumbents about entering a totally new business. So for a company like Google, the primary purpose of their chips is going to be serving an in-house business purpose. And even with all the money that they have, and even with the engineering talent, there's still a sort of trade-off question involved of how much do we want to build chips for some other purpose, for some sort of external service.
Yeah. And I also thought the point about why Sam Altman is going around talking about how he, how many billions he's going to spend was really interesting. And it kind of makes sense in the aftermath of the pandemic.
Totally.
And semiconductors, I'm sure you remember this. I think that was actually where we first learned about the bullwhip effect, and this idea that very small changes in one end of the supply chain, which would be customer demand, can end up reverberating, all the way through the supply chain. And so when you had car makers start to cut back on their orders, that had a much bigger and longer impact than you might have anticipated. And so it's interesting to see companies coming at it from the other end and saying, like, no, we have all this money and we're going to be here for a long time.
We are not slowing down. We are going to AGI. And so if you think like, oh, we're going to come out with GPT-5 and then we're going to focus on just commercializing that and selling it to airlines to do customer support after that and just go into glide mode and take business, they want to signal that they're building more and more and more. I thought that was interesting. I thought it was interesting the point about Nvidia and CUDA and the idea that, okay, yes, the CUDA software ecosystem is perceived to be this moat that makes it harder for other semiconductor companies to break into the same business, but it's also constraining from an Nvidia perspective, the idea that, okay, if they want everything to be CUDA compatible or be within the same family of software usage, then that also constrains the potential sidelines that they might get into.
Right, and opens up space for competitors. But I don't know why I haven't really internalized this lesson before, because it comes up in every conversation we do on semiconductors. But I think there's still a perception, or at least maybe I still have this perception, that the moat around NVIDIA is like the actual hardware.
Yes.
But it's not. It's the software. It's CUDA.
It seems like it's both.
Well, yeah, but I think I'm starting to appreciate how much of it is CUDA, is what I'm saying.
It certainly seems to come up over and over again, how much the fact that this is what people use, that it's the software that makes it easy for less sophisticated customers to use the applications. It seems extremely powerful. It's also interesting to hear about like the ecosystem of businesses around semiconductor design. And, he mentioned Broadcom. Reiner mentioned Broadcom, which is a company that I don't think we've ever really talked about very much on the show. But if you look at that stock, I mean, it looks kind of like you're looking at a chart of Nvidia. Like that has been a gigantic winner over the last few years. Back in 2020, it was a $31 stock. Now it's a $146 stock. Okay, it's only a 5-bagger, so maybe not quite Nvidia returns. And this idea that...
I like how Nvidia has just skewed what's
know.
expected of every stock. It's like,
but
it's on a different plane.
And this idea that a semiconductor startup doesn't necessarily interface directly with TSMC, like that's only for the most sophisticated advanced, and then there are some of these companies in the middle. I thought that was extremely interesting.
You know what, Joe? I asked ChatGPT what the most beautiful semiconductor is.
Yeah?
It says gallium arsenide is considered beautiful for several reasons. Its crystal structure is often admired for its clarity and elegance.
Oh, wow.
So I guess semiconductors made of gallium arsenide are the most beautiful.
There's beauty at the molecular level.
Yeah.
But actually, I thought when you asked that question, it's like, it's just sort of a, philosophical, fun, whimsical question. But this idea of like doing the minimum required or not building a bunch of extra rooms in the house that you don't really need. And as we know, I mean, it's just objectively true that even if NVIDIA chips are the best in the world for AI, they do other stuff beyond AI. And they do Ethereum mining, or they used to, and that was based on proof of work back in the old days. And of course, they're for video games. But if you really just want a computer, or if you really just want a model that can speak in English or write code, or can just think without doing video games and chip mining, then perhaps there are a bunch of rooms in the house that are totally unnecessary.
Yeah, and I mean, there's efficiency costs to that
costs, yeah.
You're trying to streamline it as much as possible. All right, shall we leave it there?
Let's leave it there.
This has been another episode of the Odd Lots podcast. I'm Tracy Alloway. You can follow me at Tracy Alloway.
And I'm Joe Weisenthal. You can follow me at The Stalwart. Follow our guests, Reiner Pope. He's at Reiner Pope. And Mike Gunter. He's Mike Gunter _. Follow our producers, Carmen Rodriguez at Carmen Armin, Dashiell Bennett at Dashbot, and Cale Brooks at Cale Brooks. Thank you to our producer, Moses Andam. For more Odd Lots content, go to Bloomberg.com/oddlots, where we have transcripts, a blog, and a newsletter. And you can chat about all of these topics 24/7 in the Discord, discord.gg/oddlots. There's even a semiconductor room in there, so you can just go there and just talk about chips all day if you want.
And if you enjoy Odd Lots, if you like it when we talk about what the most beautiful semiconductor is, then please leave us a positive review on your favorite podcast platform. And remember, if you're a Bloomberg subscriber, you can listen to all of our episodes absolutely ad-free. All you need to do is connect your Bloomberg account with Apple Podcasts. In order to do that, just find the Bloomberg channel on the platform and follow the instructions there. Thanks for listening.